The lecture for today is about sensors. It's a new lecture. I prepared it in last summer. Now, the issue of sensor, it's a huge sensor. I mean, I can teach a whole 12 weeks about sensors. So what I decided to do, I'm going to give a short lecture about sensors in general, kind of very short, brief overview, and it's relevant to the technology. And so the first part will be just an overview of sensors. And then I decided to present today two types of sensors, because I cannot present all sensors. So I'm going to talk about touch sensors. So finally, you will understand how this works, how touch screen works. It's an interesting MEMS devices, micro electromechanical system, but I'm going to talk about the technology of it, because this is a class about technology and how we make it and what are the processes involved. And this is an interesting case of integration, because there is a lot of nanotechnology which is actually part of the modern days cellular phones. And the second part will be electrochemical sensors. And again, the reason, and I'm going to focus about nanotechnology and electrochemical sensors. I'm not going to talk about optical sensor, gas sensors. There are many types of sensors, but our time is limited. So just introduction to sensors. This is what we are going to talk about today. And practically, you've seen this slide many, many times. We have things natural and things nano-made, and we are talking about a scale from atoms to cells. So we are talking about a huge scale when we talk about nanotechnology, and this is kind of an overview. And sensors are everywhere. And one of the reasons I decided to introduce sensors for this class, and this is for the first time, because usually we talk about transistors, but what's happening now is the revolution of the Internet of Things, where you put sensors everywhere and you integrate them with existing technology. So since sensors are going to be a huge part of our everyday life, and I'm talking about sensors, about microfabrication of sensors, integration with CMOS, and also very important, relevant to this class, the introduction of nanotechnology, and also with microtechnology, but also with the issue of networking, which is relevant to the Internet of Things. Now, you can find sensors everywhere. I mean, you can find gas and oil exploration. People use today sensors that can go down a few kilometers into the earth, and this is part of the drilling system. And today, if you talk about people doing oil exploration and gas exploration, they use very sophisticated sensors which can transmit information during drilling and also during not only for the exploration but past the exploration. And this is some project I developed sensors for this 25 years ago, and this is very tough. It's a very tough material choice because it's a very hot. When you drill to such high depth, there's a high temperature, pressure, vibrations, so it's not trivial. And if you want to put sensors in the ground to detect if you want to find, you see this black point, this is like the Holy Grail. This is a pond of natural oil. You want to detect it, so you need to use, to detect seismic waves to detect the explosions. And we are talking about, when we talk about micro and nanotechnology, we always talk about life science. And one of the major revolutions in this, the last few years is when we talk about CMOS or talk about electronics, we also talk about life science. And one of the reasons is that we talk about devices which are not on the same scale. If you take a red blood cell, and a red blood cell is, the range is less than the range is less than 10 nanometers. And we have MEMS devices about the same size. Or if you talk about viruses, and the virus is about 100 nanometers, the size of the transistor today is like less than 10 nanometers. So we are talking about, we are in an era, the size of things in electronics and the size of things in life science is about the same. So integration between life science and microelectronics is just natural. The problem is that most of you, or same as myself, we are electrical engineers or material scientists. We are not so much familiar with biology. So I'm going to give you a little bit about the aspect of how to use it for life science without really, it's not a class in life science. This is a class, still class in engineering. But because we deal with things which are about the same size, if we can integrate them together, for engineering point of view, it's not a big problem. Actually, microbes are much, much larger than transistors. So if you know to look, for example, from the observation point of view, if you know how to look at transistors, you know how to look at microbes. So another example, I'm trying to give you today like unusual examples. So we looked at oil exploration, also space transportation, and I took this from NASA. I took this from the website of NASA. And if you look at about nanoscience roadmap, you can find out, and you look at the, sorry, I have to do it this way. If you look about the year between 2002 and today, you can find that there's a lot of nanotechnology available which are being introduced into the satellite technology and microsatellite technology, and people now talk about nanos. But the nanosatellites are not nanoscale satellites. They're still big, but they are very small satellites, and you want to put a lot of information, a lot of circuits, a lot of technology into the satellites. So people talk about nanosensor roadmap in SpaceX transportation. The one which is more fun for you is what we call wearables. Wearables is a new concept where you put your mobile not like this in your pocket, but you wear it. You put it in your shirt, you put it as part of your trousers or pants and your shoes, and it becomes part of you. So in order to make sensors a part of wearable, you have to find a way to integrate sensors with your clothes, it has to be flexible. You need to make flexible sensors. And I'm going to talk a little bit today about flexible sensors. But again, it's an issue by itself. And you are practically what you want. You want to take information from you when you run, when you sleep, whatever you're doing, monitoring. It's for healthcare, and this is it's a growing field. Now, again, in this class, we studied about diffusion, about doping, about ion implantation, about chemical vapor deposition, about sputtering. And what I'm trying to do is how to use this for this application. So this class is not limited only for silicon manufacturing. We are going to touch a little bit in the sensor of what wearables. So what is a sensor? All of you engineers know a sensor is, by definition, I took from the American National Standards Institute definition. It's a device which provides a usable output in response to a specific measurement. A sensor acquires a physical parameter and converts it to a signal suitable to processing, optical, electrical, mechanical, and then we have a transducer. The transducer is what we are going to talk about, like microphone, loudspeaker, anything which converts the physical or chemical or biological measurement into electrical signal. So this is what we are interested in. So a transducer is a device which transforms energy from one type to another, even if both energy types are in the same domain. I mean, a transducer can do electricity to electricity, but we are interested in mechanical sensors, electrical, chemical, magnetic, optics, and thermal. And transducer can be, we divide them into two families. And this is a little confusing, but please remember, we divide them into sensors,
sensors monitor the system, and actuator which impose an action on the system. So this is a general concept. That's why if you see people today working on sensors, or look at what is the most important, one of the most important journals in sensors, it's called Sensors and Actuators. Because today making sensors, making actuators are two faces of the same kind of science. You can either sense or actuate, but those are connected together. And another classification of sensor is based on the physical phenomena. For example, we talk about mechanical, thermal, optical, and others, like nuclear, or you can imagine, like in mechanical, you can measure, for example, strain gauges, displacement, measurement, velocity, measurements, accelerometer, tilt, viscometer, etc. Now, if you notice, I don't mention here how I measure it. I mention here what I measure. So these are all mechanical sensors. I can use optical sensing, I can use electrochemical, I can use... So this classification is by what I measure. This is called mechanical. This is called a classification based on the physical phenomena. The second way to classify sensors is classification based on measuring mechanism. Like I measure resistance, I measure capacitance, I measure inductance, I measure piezo effect. So this is another way to classify it. Now, we are practically looking in material science for materials capable of converting of one form of energy to another, and this is the heart of many sensors. The key for many sensors is to find such materials. And one of the large efforts today in material science at large, and nanoscience and technology specifically, is to find materials and nanostructures which can be useful for this application. So you need to invent a new material, like smart materials would permit the design of a new type of sensors, invent new nanostructures, find new properties. So this is kind of a very serious field of exploration. So let's look at the family of what we call stimuli or detectable phenomena. We look at acoustics, biological and chemical, electrical, magnetic, optical, thermal, and mechanical. These are the major functions. And for example, in acoustics, you measure the wave properties. Like every wave, you have the amplitude, you have the phase, you have polarization, spectrum, wave velocity. In biological and chemical, you like the concentration or fluid, like concentration of the components, like you look for drug concentration or toxic material concentration. Electrical, this is what you do. If you're electrical engineers, you measure charge, voltage, current, field, polarization, conductivity, etc., etc. Magnetic, you measure magnetic properties. Optical, of course, you like refractive index or reflection or transmission, all these properties, and etc., etc. So let's be more specific. One way of sensors is to use fundamental principles. For example, use Ampere's law. Ampere's law connects electrical current to magnetic field, which means you can use some fundamental laws, or like Curie-Weiss law, which is a transition temperature at which a ferromagnetic material exhibits paramagnetic behavior. So you can detect by measuring the Curie temperature or the Curie effect or other derived phenomena, you can study magnetization of materials. Ampere's law you use for magnetization, or Faraday's law of induction. You remember Faraday's law, that you have a coil, and if there's a change in the magnetic field, you're generating what's called EMF, electromagnetic force, or voltage. So you take a coil, by detecting the voltage on the coil, you can detect variations in magnetic fields. Or photoconductive effect, that when light hits a material and there are change in the material, the light excites holes and electrons in the semiconductor or
In similar materials, you modify the conductivity of the structure. So all these are physical principles. And using, one of the basic fundamental of sensors is to find the right physical effect and to use it to detect whatever you want to detect. And in this example, I actually gave you that you can use Ampere's law or Faraday's law to detect magnetization. You have to you can for the same target you want to detect magnetic properties, you can use different phenomena. For example, one of the excuse me, what I'm supposed to do now, not to close, to do this? Yes? Yeah. Okay, sorry. I don't want to. Last time, by mistake, I answered yes, and then the system was paralyzed for 10 minutes. Okay. For example, you can study magnetization by its effect on polarization of light. So you can study magnetization by using Ampere's law. You study magnetization by using Faraday's law of induction. So you study magnetic fields. So you can use several phenomena, and you have to choose which one is the best suitable for you. And remember, this is a class of micro nanotechnology. The question is, can I integrate this device on a chip? Is the technology available? For example, if you want to use the first one, a current-carrying conductor in a magnetic field experiences a force. So I need to make a current-carrying conductor. But this is easy, because on chip it's very easy to deposit metal and to make lines. But if I want to make a coil, I need to make a lot of turns. And this is very difficult to do on a chip, because the chip is one-dimensional. So I can make a spiral, but it's difficult for me to make a coil with many, many turns, etc. So these are physical. So with the need for sensors, sensors are omnipotent. They're embedded in our bodies, automobiles, airplanes. Talking about automobiles, lately people are talking about autonomous automobiles, about cars that can drive a car that can drive itself. You need sensors to do it. You need sensors for light. You need sensors for radar. You need sensors for acceleration, etc. So every time we talk about advances in life, there are always sensors are being involved. And the good news, the price of sensors is going down because they can be integrated using micro and nanotechnology with existing systems. So in the past, you buy the sensor, you buy the system, you buy the power supply, you put them all together in a big box. Today, you can put it on a 1x1 millimeter chip. Everything is connected together. Batteries included. You can put a small solar cell and don't even use batteries. Without the use of sensors, there would be no automation today. So this is what we needed. So as we talk about the measurement, let me give you 1 minute. I really wanted to give you a little bit of few definitions. I assume you've seen this before, but be patient. I want to cover all bases. So we talk about measuring output as the interaction between the sensor environment. So there's an input, I generate an output. And don't forget, for every measurement, there is an error. Imperfect design of the measurements, approximation, and it can be corrected by calibration, but we need to do calibration. The big advantage of microfabrication and nanotechnology is that you can make the sensors almost identical to each other because you're using microfabrication technology. Mask, lithography methods are excellent, are highly accurate methods. So the sensors are become one of the recent advances in the last 20 or 30 years. One of the improvements in sensors is that by using microfabrication, they are becoming very standards, very uniform. But this is again classification of sensors. We can skip it. Okay, now we talk about specification of sensors. One is accuracy, is error between the result of the measurement and the true value being measured. And then you have resolution, sensitivity, the ratio between the change in the output signal to the small change of input physical signal. You can, for example, do output versus input is fit align. And then repeatability with a precision. And don't make the mistake. You have accuracy and you have precision. Precision is the ability of the sensor to output the same value for the same input over and over again. And you have accuracy, which is how accurate you are relatively to what you want to measure, and how precise you are, which is the definition of precision is like repeatability. So if you think about it, accuracy with resolution, let's say this is your result, and this is your resolution. This you can measure this, this, and this, and this, and there is a minimum measurable signal. And this is the red one is the true value. And the black one, the large signal, is what you measure. So resolution is how small you can measure. Accuracy is how far you are from the real result. Now the question is, what is the real result? So we need to calibrate it, and how accurate is the calibration itself. So there's always should be a standard, some absolute measurement that we can trust. And it's not trivial. Now, precision versus accuracy, accuracy versus precision. If you look at here, if you look at this point, this is the target, and this is what you measure, the red one. This is called bias, deviation of your measurement from the actual value. And this is the readings can be all around. The average should be the same, but the error is larger than the target, or it should be on target. So here we are very precise, but we're not very accurate. Here we are precise and accurate. Precision without accuracy, accuracy without precision, and this is precision and accuracy. So choosing a sensor. Temperature, humidity, corrosion, size, overrange protection, all those are fundamental, what we call environmental factors. So in the environmental factors, we have to look at what the operation temperature, humidity effects, corrosion, size, overrange protection, susceptibility to electromagnetic interference, ruggedness, power consumption, self-test capability. Then you have economic factors, cost, availability, and lifetime, and sensor characterization, which part of them I discussed before: sensitivity, range, stability, repeatability, linearity, error, response time, and frequency response. So how do you specify a sensor? This is a little bit electrical engineering. First, it's the dynamic range, which is the ratio of the maximum recordable input to the minimum one. And in many cases, you define it in dBs, in decibels, which is 20 times log maximum input versus minimum input amplitude. And this is in dynamic range. It's usually given in dBs, but you can also give it in absolute value. It's okay. Linearity is the deviation of the output for the best fit straight line for a given range of sensors. Then you have the transfer function, the relation between the input to the output. Bandwidth, which you all know, the frequency range between the lower and upper cutoff frequency. And noise, which is the noise of the system. If you took the classes on noise, you know this is noise depends on the frequency, depends on the processes involved, and it's a major factor defining the minimum detectable signal. So the attributes of sensors, you talk about operating. This one I run a little faster. You have the operating principles, dimensions of variables, size, data format, intelligence, active versus passive, physical, environmental stability. So let's talk about, I have like 20 slides now. I'm running through possible sensors that you can find today in microtechnology and nanotechnology, like mechanical strain gauges. You can make them foil strain gauges, gauges which are made from foils, vibration wire strain gauges, and fiber optic gauges where you look at the strain using optics, and each one has its advantage. Example for strain gauges, for example, one of the most common one is the resistive strain gauges, where you take a gauge and by bending it, you change the resistivity due to some effect. For example, one of the effects is piezoresistance. If you take the conductors made of silicon, silicon is has a very high piezoresistant property, which means the resistivity of silicon depends on the strain. If you bend the material and there is a force applied, the resistance of the silicon changes. So technology is well developed. There are many strain strain gauges available. It's relatively pretty fast, and there are many, many types of sensors. Okay, strain gauges. Another typical strain gauge is the piezoelectric strain gauge. They are based on ceramic, piezoelectric ceramic based or piezoelectric polymer based. You have piezoresistive material, PLZT, lead, zirconium titanate, or niobium titanate are many metal oxides have a piezoelectric effect, which means they change if you apply force, they generate voltage, or the opposite, when you apply voltage, they generate force. But they can detect force because they directly convert deformation into voltage. There are polymers like PVDF, polydivinylidene fluoride, which is CH2CF2, CH2CF2, CH2CF2. If you take this polymer, or called PVDF, it's piezoresistance. Piezoelectric, sorry, not piezoresistance. Those materials have very high resolution, able to measure nanostrain, excellent performance in ultrasonic frequency range, very high frequency bandwidth, therefore very popular in ultrasonic applications, such as measuring signal due to surface wave propagation. If you make today ultrasound, probably they are using one of those devices. Another very common devices, acceleration devices, like piezoelectric accelerometer. You know that Newton's law, when you apply force, you have the mass accelerate. So if you measure the acceleration of the mass, you can estimate the force operating on your device. And you can measure displacement, or you can measure the force, which is directly relation to the the acceleration. So by measuring the force using piezoelectric effect, you can measure acceleration. Let's say if you look at accelerometers in cars today, they're using a different effect. They're typically capacitive, which means when there is motion, you change. There's a capacitor with one fixed plate and one which can move. By measuring the capacitance, you can measure the motion. You measure the motion, you can measure the acceleration. You know the acceleration, you know the force. But you can also directly measure the force using piezoelectric effect. The capacitive accelerometer they are used more today. One of the reasons they are easy to integrate them with CMOS technology. And you don't use specific materials because in typical CMOS process, you have metal, you can do the etching, you can define the device using conventional technologies. So I'll skip about the specification. Force sensing are metal foil, and now I'll run fast along the measurements. Displacement sensing, this is like a background, velocity sensing, laser vibrometry, shock sensing, angular motion sensing, MEMS technology. I'm going to skip on this MEMS technology. It's for the background, temperature sensor. I'm going to skip all these sensors. So we are going to directly to the next part of this lecture. And again, each one of these sensors, I can spend 10, 20 minutes or maybe an hour to show the details. But the common things for all those sensors, they can be integrated on CMOS using the technologies that we discussed before, using metallization, using the electric deposition, using lithography. Now, to make things more interesting and more fun, I chose something which I don't think usually you see in any class in this university, in many universities. It's touchscreen. And touchscreen actually is a very common device. It's a very interesting device because what you're sensing the position of your hand on the screen. But how do you do it? So there are two major families today for touchscreens, and I'm going to give you a little bit details. We have 15 minutes in the end of the lecture, so I would say this is kind of an interesting experiment. I choose one type of sensor, and let's go in to do a little deeper. So you can take a structure where the resistance of the material depends on the strain, or if you, in this example, when your finger touches the material, you bend it a little bit. So if you have a material which its resistivity depends to the strain, you can detect this touch. And there's another material which is, you put electrodes under, and by putting your finger, you change the capacitance between the electrodes, so you can, this is called capacitive. And there are two types of capacitive sensors, and I focus more on capacitive sensors because I want to show you later the role of nanotechnology and some interesting new nanotechnology concepts. It's called self-capacitance. Practically, this is, you have, if there is no touch, this is the capacitance, you put an oscillator and put here a conductor, and there is a certain current flowing. When your finger is touching or close to the screen, you add the capacitance of your body, which is about a few hundreds picofarads, and what happens, you change the current, and you can detect this somebody is touching. And another interesting effect in these sensors that there's a hovering effect. You don't need the reed to touch. You just have to be close enough. So you can actually touch without touching, which is a very interesting thing. The human body capacitance increases the capacitance of electrodes to ground. In the self-capacitance sensors, each electrode is measured separately. Self-capacitance is simple. It can use a single layer. So you put in the process integration, you put a layer of insulator. You can do so polymer or using glass, using chemical vapor deposition or sputtering, and then you put on top of it metal using sputtering or other methods, and then you need lithography to pattern the structure. So it's a relatively simple process. It's a long distance field projection, which means you can sense even when you are not touching, can be used with active guard. It's fast also. Disadvantage, limited to one or two touches with ghosting, which means you can only touch one point on the screen. You cannot touch few places in the same time. Lower immunity to LCD noise. The main problem that usually the touchscreen, under the touchscreen there is a screen with all the electrodes. I just show you the touchscreen, but there is a screen doing a display of signal, like liquid crystal display, and there is voltage there, and there are some noise because of that. And the touch accuracy is not so high and harder to maximize signal to noise. This is typically used in lower-end smartphones and feature phones with touch. And it's become less and less common today. It was more popular. In combination with mutual capacitance. So the next, what most of the people are moving today to a little more sophisticated screen, which is called mutual capacitance. And in this case, you have one electrode and a second electrode, and you're measuring the capacitance through between them. And when your finger is touching this area, you are disrupting the electric field. The human body capacitance still charge which decreases the capacitance between the electrodes. It's called mutual capacitance sensor. And this is how it looks typically. In using lithography, you are define the electrodes, and you can actually define the electrodes row and column. And by where you touch your finger, you can know the x coordinate, the y coordinate, and get the signal. And this one I took from 3M, and you can also, this is another 3M technology. Now, the interesting part here, you don't ask me, Yossi, you put conductors, right? But conductors are typically metals, and metals don't transmit light. So how you make a touch screen which is transparent using conductors? So the magic is to use a transparent conductors. And this is one thing I want to teach you a little bit today about the new material, not so new, but the material called ITO, indium tin oxide, which belongs to a family of what we call conducting transparent oxide, CTOs. And there are few metal oxides, which are conducting. And you can put, this is another design, this is from another company called Cypress. And this is called Manhattan geometry that you put, these are the electrodes. And as you can see in their screen, they are not all the same size. And these are not the bars and stripes, but again, the idea, it's a mutual capacitance electrode pattern. This is one design. And mutual capacitance are, you can make few more touches, much more immune to noise, accuracy is much better, more flexible to design, you can maximize signal to noise. The main problem, they are more complex, and you need at least 2 layers. So the manufacturing is more expensive. And this is how it looks, the design. Let me show you a little bit. This is not the class about layouts. This is more, our class is more materials, but you can't avoid looking at various layouts because you can, for example, this is called caterpillar pattern. So you have few electrodes like the red one and one which is the blue one. So you don't need for every pixel to make 2 electrodes. You can make 1 electrode which is shared between the whole column. And this is one method to make touchscreens. Another family of touchscreens are what's called pressure sensors. You actually put, for every pixel, you put a pressure sensor. Now, if you look at the bottom, it says multiple startups are working on smartphones pressure sensing today, which means it's not yet out in the market. I identified 2 companies, Max Input and called Floating Touch. They make pressure sensors. So every pixel is a pressure sensor. But it's for some manufacturing problem. So it has never been implemented successfully in a mobile device. Only the BlackBerry used it and one of the NISA, Pertec. So it's a very rare device. So how do you make this touch sensor? You need to have indium tin oxide. Indium tin oxide is the material of choice today, which is a conductive transparent oxide. You make the thickness of the film on PET. PET is polyethylene terephthalate, or COP, it's cyclic olefin polymer. Those are the 2 polymers of choice. Thickness is about 100 to 50 microns, and the resistivity is typically in the range of 100 ohm per square. And another interesting material in the display, which I'm not going to talk about it today, but by itself it's very interesting, is the glass itself, because in many cases you have the glass, and some makers develop thinning process to reduce glass thickness to 0.2 millimeter, like Corning and AGC, 100 micron thick glass, but it hasn't been used in volume manufacturing. And ITO, indium tin oxide on glass, I put here 100. People can go down to 50, but not much better. So from materials point of view, the touchscreen you can put it on glass or put it on plastic. If you put it on glass, you can go to very high temperature. If you put it on plastic, PET, you can go only to 70 C. Glass is no aging effect. Plastic, you have yellowing effect. Transparency, glass is typically better than the plastic. So in general, the only reason to go to plastic is cost. So let's move on. I need a material that will have a good transmission, good thickness to weight, good border width due to routing, because I need to put on the side of it, I need to put all the interconnects, cost and availability of ITO film of the position, lamination. Lamination is a process when we put layers on top of it, and I want to use existing equipment. I don't want to invent new tools. So glasses, what people usually do, they take the mother glass, they make a big piece of it, they do the border patterning, then do the traces, then they cut the glass, grind around the glass, and then integrate it. This is one process, and the screen manufacturing class, it's what's it called, the mother glass, and then they cut the glass and ITO patterning on top of it, sensor glass, and then the attachment, and then put the cover and integrate it, and typically it's a cell phone. So how to make a glass hard? I believe you all heard about the term called Gorilla Glass. Typically, you have 4 processes today to make hard glass. One is heat strengthening. It's a less rigorous version of a fully tempered glass, does not dice when broken. It's about twice as strong as a standard glass. Fully tempered glass is that you take the glass to high temperature, use heat. It has to be relatively thick, more than 3 millimeters, so not used for consumer touchscreens. It's pretty strong, 4x to 6x as standard glass. And then you have chemical strengthening using ion exchange in a salt bath, best for glass, less for a thin glass. Glass does not dice when broken. It's a 6 to 8 times as strong as standard glass. And high ion exchange aluminosilicate glass, this is what we call the Gorilla Glass. By the way, Gorilla Glass is a trademark of Corning. Asahi call it Dragon Trail, but it's just the name. And the idea is an ion exchange. You dip the glass inside an electrolyte and you apply electric field, so some of the ions penetrate into the material and strengthening it. And it's 6 to 8 times as strong as a standard glass. So this is the Gorilla Glass. And historically, most common treatment is anti-glare. People also put anti-glare on top of it, and anti-fingerprint on top of it, and anti-reflection and other coatings, etc., like also antimicrobial, if you don't want any microbes to be deposited on your structure, and hard coatings, and anti-stiction, so nothing will stick to the glass. So I want to talk about materials today, because this, again, let's focus on the materials part. How to make transparent material which conducting. There are practically the best solution today, there are a few best solutions. One of them is to use transparent conducting oxides, like arsenic-doped tin oxide, ATOs, tin-doped indium oxide, ITO, aluminum-doped zinc oxide, AZO, fluorine-doped tin oxide, FTO, and niobium-doped titanium oxide. I would say the most common today is ITO, but it's a big problem. It's a big problem because the cost of indium is going through the roof. And it's becoming a significant part of the cost. So there's a lot of effort today to develop alternatives. Zinc oxide is one of them. Aluminum zinc oxide is one of them. Zinc oxide is also a candidate. This is the transmittance of zinc oxide. And you can see it starts at ultraviolet, and this is the transmittance. And it's pretty good in the visible range. So zinc oxide is actually a pretty good candidate.
At indium tin oxide, this is absorption, which is the opposite of transmission. This is a very low absorption, down to about 350, so it's also very transparent in the visible range. ITO itself, it's a cubic big byte structure, like indium 203, and you have two sides, two available sites in this structure because the two cubes are not exactly identical. And ITO is a direct band gap, and you take this indium oxide and you dope it with tin. This is called ITO, tin-doped indium oxide. It's a direct band gap semiconductor with a band gap in the range of 3.5 to 4.3 electron volts, depends on the concentration of the indium and the tin. How do you deposit ITO? One of the most successful, there are two very useful methods. One of them is reactive sputtering. You remember we studied sputtering. We say that we take ions and the ions bombard the target, and because of that we sputter atom and they deposit the wafer. But let's imagine that the gas, instead of being inert gas during the sputtering, I introduce a little bit of oxygen into the chamber. So the target, which is indium, is being bombarded by oxygen. And then indium is sputtered, but in the volume of the chamber there is oxygen. So what is being deposited is not indium, it's indium oxide. This is called reactive sputtering. It's actually very useful to deposit metal oxide. We have few tools like this. You can take a target of metal and sputter it in an environment which contains oxygen. Then we can do tungsten oxide, titanium oxide, and this is how people do indium tin oxide. By the way, if you can add some nitrogen inside, then you will get nitride. Or you can put oxygen and nitrogen and you can deposit oxynitride. So reactive sputtering is a method that you use sputtering, but in the volume of the chamber you introduce reactive gas, so you have chemical reaction after the sputtering in the volume and you deposit the outcome. The other way is a chemical deposition using the sol-gel process and a chemical bath. Chemical bath deposition, you take salt of indium and react it with another compound, and you have to reduce the ion into a metal or to oxidize it, and then you get the oxide. Or you can use chemical vapor deposition, as we studied in the class. And there are two, it's a plasma enhanced CVD, not VBD, so I have to change it. PECVD and atomic layer deposition. I will skip these two materials. I will skip to this and we'll go to the next. What will replace ITO? ITO become very costly. And replacement, I'm going to steal 5 minutes of the next lecture because I want to finish this. There are 5 replacement candidates. One of them is the metal mesh. Metal mesh is kind of a new technology, appeared first time 2012. And the idea, instead of put a layer of metal, you put thin wires of metals, and this is a metal mesh. Now metal mesh is quite transparent. And you can design it, the conductivity, to be even better than that of ITO, because conductivity of ITO is, as I told you before, it's 50 to 100 ohm per square. Conductivity of most metals in this thickness of few microns is 0.1 or 0.01 ohm per square. So if you put a metal in this structure, you can get effective resistivity better than indium tin oxide, and then it's pretty transparent because most of the glass is not connected. So how do you make the metal mesh? For example, one of the easiest way to make metal mesh is to use a technology that, if you remember the lecture on lithography, I told you about imprinting. Take plastic, put resin, which is a polymer, then you take the negative and imprint it into the polymer. Then you deposit on top of it silicon nanoparticle, ink, and cure it. And what you have is a silver nanowires embedded
inside the plastic. So this is nano imprinting or imprinting or micro imprinting lithography. This is how it looks. By the way, one of the leading companies is Sima Nanotech, which was an Israeli company, being purchased by another company. You deposit the metal nanoparticles. Initially, it's opaque, but as the nanoparticles coalesce, you have a random pattern, silver mesh, and this is how it looks. The silicon the nanoparticles, what they do, when you know, initially the nanoparticles is like a drop. You put them in an ink. So when the ink dries, most of the area is, sorry, I confused you. So this is the roll-to-roll printing. This is the silver nanoparticle mesh. And the idea that if you put a silver nanoparticle and you mix them with a liquid, now the liquid dries, what happens, the silver is concentrated only on the side walls of each bubble. For example, this technology, which is called silver nanoparticles, it's another Israeli company called Clearjet. This is Professor Shlomo Magdassi from Jerusalem Technology. It's called the coffee stain method. Take a drop of liquid with nanoparticles. It's being deposited, and if you ever dropped the coffee unintentionally, of course, on the table, and you see when the drop dries, most of the coffee is on the sides of the. You get a coffee stain. Coffee stain is not uniform coffee; it's just like a ring of coffee because of surface tension. The particles are being expelled to the periphery of the drop. So what happens when you take nanoparticles mixed with liquid, you make a drop, and let the drop dry, what happens, you got this ring. And these rings are connected. And every ring has a lot of nanoparticles in it, and it's conducting. You can also use carbon nanotubes for it. And I'll skip and this is the display, and I think it's 6:05, so, sorry, it's 4:05, so we'll go to 10-minute break and we'll continue with these sensors later. Continue, but let's review a little bit the last lecture. So what will replace ITO? As I told you before, indium tin oxide is it's a very good material, but it's costly and needs high temperature processing, so it might be a problem to deposit it on plastic. And it's a very high reflective index, which I didn't mention. It's a little bit tinted yellow. It's a little bit, has a little bit of a yellowish color. But it's not because we are running out of it, just we need alternatives. So replacement material objectives. People want to look for solution processing, not vacuum. Vacuum processing is expensive, solution processing is less expensive. In my lab, for example, we investigate zinc oxide as an alternative, and zinc oxide, you deposit it from a liquid bath, you take zinc nitrate, you dissolve it in water, you mix it with a reducing agent, and then you have a reaction between the zinc nitrate and the reducing agent, and the result is a zinc oxide deposition. It's a very cheap process, and it seems like this is going to work for a few materials. Better performance than ITO, and lower material and process cost. This is the main issue. So I showed you the metal mesh, which was first introduced in 2012. By the way, it was not, it didn't go to the market because the factory was burned down, so the company was closed. So it was a good product, but nobody used it. Atmel introduced it later, and it's actually, people use it, some companies use it for smartphones and 7-inch tablets, and Fujifilm started production of the silver halide-based metal mesh product in 2013, and they have few screens in the market with metal mesh. And again, you have metals going one way and other way, so you are generating a mesh. And this specific one, it's a 4 to 6 micron wide conductors with spacing about 100 to 400 microns. So only less than 1% of the surface is covered with metal. And the advantage of this technology is that you can actually make it on very large areas. So metal mesh has significant advantages. Patterning, you can do roll-to-roll printing, allows both operating and capex cost. Capex is a capital expenses. A capital expenses means cost of equipment. Capex is a very fancy name to cost of equipment. A cost of investment, it's very low. It's going to beat both litho and lasers. Electrodes and border connections are printed simultaneously. Sheet resistance is much lower than ITO. Actually, people get today less than 10 ohm per square. And reduces the, if you remember, we talk on the proximity capacitor that we have 2 electrodes and our finger touches somewhere in between, so we change the capacitance between the electrodes. So it's actually because of the much better resistance, it's much lower resistance than ITO, the charge time or discharge time is faster, so this screen has much better response time. And transparency is better than ITO, and mesh pattern creates electrical redundancy, which improves yield, and highly flexible. You can make what's called bend radius, typically 4 millimeter. Now let me tell you, how do you measure flexibility? There are a few measures. People are flexible, it's something I can bend. Not, can you give something more tangible? So one way you can say, people say, I can bend radius to 4 millimeter, which means I can deposit this mesh on a polymer and bend it to a circle, and the circle diameter is 4 millimeter, and everything works well. Smaller radius, it will break. So it's not very scientific terminology, but many people quote like size, what is the smallest diameter I can make of a flexible substrate without causing some traumatic effect to the film. One way, it's called, like for example, the O-film, which is a commercial name, or people call it the 800-pound gorilla, or in Hebrew you say 2-ton gorilla, which means this is one of the most workable solution. The largest touch module maker is in China. It's practically, you take the polymer and you insert the metal wire inside the polymer, and the method I showed you before is that you take the polyethylene, the PET, put a polymer, you use a metal roller to print the trenches, fill them with silver nanoparticles, and cure it, and you have this screen. So this is the one option. The second one is the nanoparticle mesh, and this is called self-assembling methods. You take nanoparticles and you mix them with liquid, and then they self-assemble. And in this specific design, they self-assemble into wires, and the wires are all connected. So this film is practically conducting because the current can flow through the wires, but most of the open area is open, and this is how it looks from a side view, and this is how it looks from a top view. By the way, most of the connections are triangular, and the angles is approximately 120 degrees. But it's a random mesh, and it's actually a pretty clever solution. A second option is to use silver nanowires, and this is like the game, that you make the nanowires and throw them on the table, and they, by randomly, generate a mesh, and this is called silicon nanowire. This company, Cambrio, they make silicon nanowires and kind of throw them on the plate, vibrate it, and you can have this coating. And this is how it looks. You can make them 70 ohm per square and 9 ohm per square. Its density determines sheet resistance independent of coating throughput. And it's pretty transparent. So this is a company that makes transparent
conductors. And the Israeli company Clearjet use inkjet printing silver nanoparticles drop, less than 10 micrometer thick. The ink dries from center outwards, leaving coffee rings about 100 micron diameter, 95% transparency, 4 ohm square resistivity. It's one of the best solutions today in the market. It's a startup company which is actually quite successful. Now, instead of using metals, you can use carbon nanotubes. Carbon nanotubes are conducting. And you can use, and this is a film of carbon nanotubes. And you can actually print them on the polymer structures and get randomly distributed nanoparticles, all connected, and to get some, and in this specific system, you introduce carbon gases into the reactor. You work under the condition that the carbon is being deposited. This is a chemical vapor deposition of the carbon nanotube, and it's the specific process. I will not go through the detail how they actually grow, but you insert the gas inside, apply temperature, and the carbon is being deposited in a very unique film, a very unique form called carbon nanotubes. You need to have some seed of metal on the bottom. And the carbon nanotubes, this is this company. You can actually make, this is the carbon nanotubes in combination with buckyballs, so they call it like the nanobuds. And these structures better optical performance than silicon nanowires. It's more flexible. The bend radius is 0.5 millimeter. They call it the nanobud reactor. And they actually do the patterning using laser patterning. Now, there are other materials which are conducting. There are special classes of polymers called conjugate polymers or conductive polymers. This specific polymer is P-DOT, PSS, but there are other polymers like polyaniline and polypyrrole. But the advantage of P-DOT PSS, it's transparent. It's made by a few companies, and it started only about 3 years ago. The resistivity isn't much different than ITO, but it's easy to apply because you can also use screen printing. Screen printing is like people make prints on shirts, put the pattern, put the ink, and wipe it out, and sorry, you got the deposition. So you can actually use it the same way as people paint shirts. It's a very low-cost process. White goods manufacturing can use it to make their own touch control panel in appliances. The other material which has not been introduced in touchscreen is graphene. People are talking about graphene for touchscreen. I couldn't find any reference, but maybe I didn't find. But the resistivity and transparency aren't there yet. So people talk about it. I didn't see any publication. The display itself, if you think about it, I gave you the outline how to make the conductors. The insulator, you can guess, we can make it from polymers or chemical vapor deposition, but under it, there is the screen. You have the backlight and the light guide on the backside, the backlight and the light guide, and then you have the brightness enhancement film and the bottom polarizer, the TFT glass, the TFT array, the thin film transistor array, alignment layer, the liquid crystal here, another alignment layer, transparent electrodes, then the color film for the colors, because every pixel you can illuminate, you can make it red, blue, or green, and then the top polarizer. So this is typical display when you have, this is typical the structure of a liquid crystal display where you are illuminating from the back side. And on top of it, you have in this every square here, there's a transistor that can, when you apply bias to it, you can switch this pixel, and you can let it either path light or don't path light. So it can be illuminated, it can be dark or bright, and it gets the color based on the color filter on top of it. So practically every pixel is different color, but a few pixels together are
effectively one color pixel. And typically can be 9 pixels or 16 pixels with a combination of green, red, and blue, and this gives you the color. And on top of it, you need to put the touchscreen with the technology I showed you before. Now, by the way, if you talk about, I don't think that we talk about liquid crystal display, but just for general intelligence or general knowledge, there are two families today of one called IPS and the other. And the IPS technology, you are practically, you have electric field. And it depends how you apply the electric field. Either you apply it from an electrode, from this electrode to this electrode, and this affects the liquid crystal molecule, so it affects the transmission. So either the polarization is in the wrong direction, when low light is going. When you apply electric field, the polarization rotates by 90 degrees, and there is light through this pixel, because now the light is going in a certain polarization, and if the polarization of material is perpendicular, there's no light is going, but if the polarization is in the right direction, practically the light can go through this, so this is called the IPS. The second technology, when you put the electrodes on the two sides, and this is the off, when this polarization practically blocks the light, and this polarization, when you apply electric field, the polarization rotates, and the light can go through. IPS is considered as better quality, a better resolution. You can get better resolution, a smaller pixel, etc. But those are the two common architecture. Either you apply voltage between two layers, or you apply between this and this layer and put the liquid crystal in between. And just to give you some example, you can also introduce light using OLEDs, organic light emitting diodes. And the first device that integrate OLEDs and all on-cell proximity capacitors. Remember, I told you there are two methods for sensing. One is the self-capacitance. One is when the electrodes are on the same. So this is what's called the Super AMOLED. This is, I don't want to make any commercial to any company, but this was the first one that introduced the screen and the touch screen on the same one. This is called on-cell pickup. When you have thin film transistor on the bottom, because you need to switch the polarization, so you need a transistor to select. You put on the gate, select, and voltage on the drain, then the source is connected to the electrode to bias it for the selection of the. Then you put color filter, and on top of it, you put the cover glass. And the first form is hybrid in-cell, on-cell mutual capacitance. It appeared about 5 years ago by two companies, the Sony and the HTC, Evo. And the iPhone 5 was the first fully in-cell mutual capacitance, which means everything integrated. By the way, there's an argument because this appeared March 2012, and this is September 2012. So this is hybrid in-cell, on-cell mutual capacitance, and this was a fully in-cell. Everything was integrated on the same screen, not two parts together that you mix them. So this is an innovation in iPhone 5. And the actual electrode structure looked like this. It's using ITO. You have two types of ITO, and then also a dummy ITO for the load. By the way, just most of the time I talk about capacitive touchscreens because this is the most popular. There are other things like in-cell light sensing. People use LEDs, and by touching it, you change the reflection. So practically, you can put a photosensor, and you can detect when you touch it. Photosensor added to each pixel. You can use infrared sensor, amorphous silicon added to the thin film array. infrared emitters added to the backlight, does not depend on the ambient light. The advantage of this one, you can do it in dark. Has an original design, actually it's a pretty old one, works with finger or light pen, can work as a scanner. Adding a cover glass to protect the surface of the LCD touch sensitivity because the finger is farther away from the sensor. So it's actually, you can use high cell press capacitance. This is another method that you can actually, this is the glass. When you touch it, you are pressing the LCD, changes the electric constant of the liquid crystal, which changes the capacitance between the conductive column spacer and the flat electrodes. Electrode pair can be on pixel or a group of pixels. Works with any touch object, so this is actually also another innovation being investigated. In-cell voltage sensing, also called switch sensing or resistive, that you are pressing the LCD surface, closes XY micro switches in each pixel or a group of pixels, requires deflecting the LCD surface, cannot add a cover glass, works with any touch object. In-cell self-capacitance, it's another thing, and this is it we finished the subject of touch screens. Okay, let's open. No, yes, small. I made one change. Okay, let me close it. 1 minute, okay? Good. So now let's lecture number 2. It's actually lecture number 9. Electrochemical sensors. We have about 1.5 hours until the end of the lecture today, and let's focus on electrochemical sensors. And I decided to choose them because it's a combination of processes and technologies which are very relevant to the class. Again, I'm not talking about gas sensors and other sensors, but let's at least take one topic and cover it. And now, since most of you are not experts in electrochemistry, I just put here some suggested electrochemistry texts. If you want to know more, this is a list of books. And I took this lecture from the professor of Steven Feilberg from Monash. I took a lot of slides from his lectures on this field. And these are recommended reading material relevant to electrochemical sensors. Now, before we talk about electrochemical sensors, I want to have like a 10-minute review in electrostatics and electrochemical potentials and fundamental physics of liquids. And because I know that most of you, is there anybody here from chemistry? No, anybody from material science? Yes, so material science, we cover it. In electrical engineering, we don't cover it much, but you can find out that it's nothing new. It's very easy to understand. The idea is that we are dealing with charges, and we want to detect charges. So the topic today is relevant practically to sensors which detect charge and detect potentials. In electrostatic neutrality and quasi-neutrality, we have to understand that in most of the situations, we can define neutrality when the positive charge density is exactly equal to the negative charge density. And quasi-neutrality is when the positive charge density is almost equal to the negative charge density. The difference can be neglected for all practical reasons. Now, in many cases in life, we are dealing with quasi-neutrality. We all studied semiconductor physics. Semiconductor physics, we have electrons and we have donors. Like, for example, in an N-type semiconductor, we have donors and electrons. The donor gives the electron. The electron is traveling everywhere. The donor is fixed. On average, the number of electrons is equal to the number of donors. So on average, the positive charge of the donor is equal to the negative charge of the electrons. Now, additionally, we have holes. So holes contribute positive charge. So when you look at all these salads of electrons, all these charges, we say that On average, the total charge is equal to 0. The total number of positive charges is equal to the total number of negative charges. But if I look very close to the atom, I see a donor, which is positive. If I look very close to the electron, let's say I increase my magnification, the electron is negative. So next to the electron, the charge is negative. Next to the hole, the donor, the charge is positive. The local charge separation generates a dipole. Anytime I have a positive charge and a negative charge between them, there is a dipole. And the dipole preserves neutrality, because if I want to separate them, there is a force between them, making them moving back together. So the dipole is the driving force for neutrality. And dipole generates local electric field. Now, you all know from elementary physics that electric field is the gradient of the potential, or d phi over dx in one dimension. So let's talk about capacitors. Capacitors, you all know. Two plates. We put voltage 0. There's no charge between them. I apply a voltage potential between them. Let's say I put a positive V, and I have a charge Q. So in all, we know that the sign convention, that the positive charge moves to the positive direction in a positive electric field. So you all know, we all studied electrical engineering. And we know the rules. We know that the displacement D, vector D, is epsilon times electric field E, which is Q over the area, charge per unit area. And the capacitance is equal to Q over A times the potential, or epsilon over delta. Delta is the separate distance between them. We all know the capacitance per unit area is epsilon, the electric constant, divided by the distance between the plates. So far, nothing new. Now, you do the same experiment in air. This is what you get. Now you take water and put some sodium chloride, some salt inside, or take some blood, or take some electrolyte, and put this inside the electrolyte. You see that the capacitance changed dramatically. It goes up by orders of magnitude. What happens? The electric constant of water is like 80, so it should increase by a factor of 80, but it's not. It's much, much higher. And also, it becomes independent of the distance between the plates. What's happening? So the capacitor, in a typical capacitor, the voltage, if I apply a fixed charge, the voltage between the plates is proportional to delta. So V is the charge divided by the capacitance, which is charge divided by epsilon times D. So this should be a straight line. Or charge in a constant V, charge is 1 over the distance. We all know these rules. So this is C is epsilon over delta. Delta is the distance between the plate. Charge is A times voltage times C. And we all know the voltage is Q delta over A epsilon. This is fundamental. What happens if the electric material is in electrolyte? The capacitance is almost independent of the distance between the plates. But the liquid is electrolyte. It's not conducting electrons. What's happening there? What else you see, the capacitance is much higher than what is expected from the previous equation. I cannot apply the previous equation if I put electrolyte between the electrodes. The previous equations are good only if there is air between them, or gas, or an insulator. But if I put electrolyte, which is water, it does not conduct current, but nevertheless, if you put water inside, capacitance will increase dramatically. Why? Okay, introduction to electrochemical potential. Let's remember law of Kirchhoff's law. Kirchhoff's law is, or if you take two materials, and each material has a different electrochemical potential, and for all of you which are not familiar, electrochemical potential is what we call Fermi level. Fermi energy, in physics we call it Fermi energy. The chemists call it electrochemical potential. So if the Fermi level of metal 1 is higher then the Fermi level is metal 2. What will happen when I connect them together? Electrons will go from high energy to low energy. So they want to be in equilibrium, right? So they will reach equilibrium. But if initially they were in different Fermi level, what happens, now the Fermi level is different, is the same between them, but what's happening there? So now let's look at the work to move a test charge from any point in the system to infinity, and we know that, you know the rule, that if I take an electron from here to infinity, it doesn't matter if I go like this, or go under the table, or go through the wall and to the roof. The energy from here to infinity is independent of the path. This is one of the basic laws in physics. So if I take M1 and M2 and connect them together, and I want to take electron from here out, I need to invest a certain amount of energy. Then I take this electron, move it from here to here, and then I move it out. I need to spend the same amount of energy. So if I go from here to here, from here to outside, either directly or go to the next area, and then out, I should spend the same amount of energy. Now, in engineering, we say that the potential difference between here and here is independent if I go from here to here or I go like this. Which means, note that there is an electric field, and note that there is an electric field outside the metal. And what happens if I take these two materials and connect them together, and I keep the same, pay attention, they are both in the same temperature. Right? Be careful. Everything I'm going to say now is assuming there is a thermal equilibrium. That they are all in the same temperature. There's no temperature difference. The difference in the partial molar free energy, or the difference of the Fermi level, what's happening if the electrons want to go from here to here, there's less electrons here. So this area is positively charged, and this area is negatively charged. If you remember, when you put N-type semiconductors or P-type, electrons are going from the N-type to the P-type. But even if you have two metals, and one with higher Fermi level, one with lower Fermi level, electrons will go from the higher to the lower. So you will generate some electric field because you have initial flow, but this initial flow is not forever. This initial flow by diffusion, by the difference in the potential, will be balanced by the formation of electric field inside. So we can define a different potential between 2 and 1 is the Fermi potential here minus the Fermi potential here. Now, when we deal with electrons, usually we say electron volt per electron. But when we deal with chemicals, in chemistry, we usually, the unit of measurements is mole. Mole, if you remember what is a mole? What is a mole? 1 mole. How many molecules you have for 1 mole of material? No, how many atoms or molecules you have in 1 mole? Remember the number called Avogadro's number? There's a fixed number. So the problem is that when we deal with electrons, there's 1 unit. But if you want to look at number of electrons per mole, or number of charge per mole, we have to derive it by a unit called Faraday constant, which is how many electrons per mole. How many coulomb per mole, sorry. Now, if mole is Avogadro's number, which is 6 times 10 to the 23, and 1 electron is about 10 to the minus 1.6 times 10 to the minus 19, so I have to multiply the two numbers, and I get how many coulomb per mole. If I take 1 mole of electrons, how many coulombs I have. So this is the number. So, but it's just a conversion ratio, because you can calculate the potential in electron volt, or you can calculate the potential by electron volt per mole. It's the same. It's just units. So can the potential between points 1 and 2 can be measured? How can I measure the potential between 1 and 2? You tell me, oh, you can put a voltmeter. No, you cannot put a voltmeter. Because if you put a voltmeter, you have to put here, let's put a voltmeter, okay? So the voltmeter is made of another metal. Let's call it M3. So let's calculate what the voltmeter will measure. What it will measure, by the way? Hint. We have to, what happened if there is a voltage at equilibrium and a current in equilibrium? It will be a perpetuum mobile. So I cannot have a voltage here because we are in equilibrium. But let's see, let's prove it. The voltage here is the difference between the potential here to this, plus the potential here to this, plus the potential here to this, and the total will be 0. Because we go back in circle to the first point. Which means I cannot measure the potential between M1 and M2 by just connecting here a voltmeter. Because I will get 0, because we are in equilibrium. We are in steady state. No, sorry, we're in equilibrium. So I have to, it's not going to work. Another idea? How do you measure potential between, by the way, this is called bimetal, or when you take two materials and connect them together. We have to be smarter. We have to find, for example, this is a very interesting method. It's not so useful, but in practice, some people use it, but it's difficult to execute. But what happens if I take our voltmeter and put it here, and put here two electrodes which are the same as this one, and connect it this way, and I take this distance delta, and I vibrate it. Have you seen this trick before? It's called Kelvin probe. You have to see what if you vibrating this capacitor, the capacitance will change, right? The capacitance will also change. It will be also periodic, because the capacitance is epsilon divided by the distance. And if I take, I mechanically vibrate it. So what happens? The capacitance is variable. Then what you do, you change the potential so that what happens is when you change V, you're generating a current here, because the capacitance is changing. And because the capacitance is changing and there is a voltage, the charge is function of the voltage and the capacitance. And then what happens, you are measuring the potential where di over d delta equal to 0. What happens, you find out that when you change the voltage at some conditions, di is positive, di over delta is positive, and some potentials, di over d delta is negative. And you find out that at this point, when di over d delta equal to 0, it's only when this capacitance voltage is equal to 0. When this voltage is equal to 0, then we know this is 0, which means this is when phi12 equals phi21. So this voltage that I measure here is phi12 or phi21. So the experiment is doing like this. I change the voltage, I sweep the voltage, and I look at the change of current, but the change of current is a function of delta. And I look for the point when this function is a minimum or a maximum. This point gives me V capacity. I'm not giving you the proof. Go Google it. Proof is very simple, but you can have two ways to do it. One is to write the formal equations and find it. Second one, think about it. That what does it mean di over d delta? D over d delta, di is discharge, I is discharge per dt. Now this will be equal when the charge here will be 0. The charge here will be 0 when the this capacitance will be 0. Now, with voltage, but this voltage between here and here is 0. And when this voltage between here and 0, the potential here equals to the potential here. And then the total potential, because the total potential is 0, then I got this voltage is equal to phi12 or minus phi21. It's a very tricky method, and it has one problem. And this is the basic to the Kelvin probe, and you can look at this paper from 1997, where it was implemented. And we use it, by the way, we use it in the lab. It's an analytical method which is popular to measure potential, and this is part of the sensor, electrochemical sensors. The problem is, we have a problem here. With one thing we didn't take into consideration. So always there's a problem. When I give you this lecture, there's always, I give you to the point, there's a problem. The problem here is that I assume that the charge here is fixed. I neglected surface charge. I assume that all the charge is just in the metal. I neglected the problem that here I can have on these two electrodes, can be dipoles, which means because there's a dipole, the dipole does not change much the voltage because it's infinite, but it changes the charge. So if there's a dipole on the surface, the whole assumption here is not valid. Okay, so what happens? So I gave you a solution, but now let's leave this problem aside and see what happens. I want to make sensors in liquids, right? So what happens when I put a metal, a non-reactive metal, in salt solution? And I intentionally write here non-reactive metal, like gold, platinum. I don't want to deal with chemical reactions. I want to stay in electrochemical reactions. If there's some chemical reaction, this is another lecture. So what can be said about the interface? The electrolyte is neutral, but the surface of the electrode can be charged. And they'll be charged because there is a difference between the Fermi potential in the metal and the Fermi potential in the electrolyte, or what we call it electrochemical potential. So if the so what happens? The surface will be charged. An electrode which happens to have taken and this specific one, the electrode will be more positive than the solution. It can be also the different. Depends on the solution, depends on the metal. What can be said about the interface? Can its potential be measured or controlled? So let's do the same what we did before. We put two electrodes, and in this case, what I'm doing, I put one big electrode, and this is the second one, which I call it like ideal electrode, or I don't care electrode. It's like by the way, this is it's in a practical application. I have to take care of this. So what happens if I take this electrode and I put here a voltage which is negative, then the electrode will be negative and the solution will be positive. If I'm in an ideal situation that the electrochemical potential of these two materials is the same, then if I put a 0 voltage, then the charge here will be 0. And if I put here a positive voltage, then the charge here will be positive. But as you can see, the capacitance is between the metal and the solution. It's not between this metal and this metal. And this is the key to electrochemical sensors. We are not dealing with, we have two plates, but the capacitance is between the plate and the solution. So what happens when a non-reactive metal is immersed in a salt solution, which also contains a redox couple? Now, I want to sense something. One of the most fundamental sensors are sensors which can detect very simple chemical reactions. Like, for example, in diabetes, you want to detect a presence of hydrogen peroxide. You want to detect, you have a molecule, OX, that plus electron, you oxidize. So you reduce the you reduce this molecule. There are some, in electrochemical reactions, you can give electron or take electrons. Giving electron is called reduction because if it's a metal, the charge is going down. If you take electron, it's called oxidation. So now there is a mechanism for moving electrons between the metal and the solution. There is a thermodynamic mechanism establishing a well-defined interface potential. The potential difference between here and here is the difference between the Fermi levels. If you remember when we talked about MOS capacitors, we say that in equilibrium, the potential between the metal and the semiconductor is phi ms, we call it, the potential of the metal minus the potential of the semiconductor. Same for electrolytes. The potential difference between the electrode and the solution, or the redox in the solution, is the difference in the electrochemical potential. The interfacial charge separation will be exactly that required to produce the potential, this potential required for equilibrium with the redox system. Now, Nernst equation. I mean, it's a very important equation, so I give it its own definition. The Nernst equation indicates the ability of a redox couple to donate or accept electrons. This is directly related to the electrochemical potential. It is expressed as the potential of the electrode via some reference potential. And if you see here, if you have a reaction that you take electron or give electron, the potential of the reaction minus the reference potential, or delta, the change of the potential, is RT over NF. Now, RT over NF, RT in engineering unit, we usually write KT over Q. In chemical units, it's RT over NF, but it's the same units. It's about, in room temperature, this is 25.6 millielectron volts, times ln of the concentration, the ratio of the concentration between the two species. Now, I don't write here concentration. The chemists usually call it activity. But if you don't go to very high concentration, this is the concentration of the two species. Now, you all remember it in a diode. If you remember in a diode, the electrochemical potential is KT over Q ln over N divided by, we define the Fermi potential, which is KT over Q ln P over, it was P over Ni, or N, or P over Ni, or N over Ni, depends how we define the electrochemical potential. In solutions, we have, instead of electron and holes, you have oxidation species and reducing species, and the potential of the electrochemical potential depends on the concentration of the oxidizing component to the reducing components, or the concentration ratio between the oxidizing species to the reducing species is e to the power NF E redox minus E0. In solid state physics, we usually write e to the power of Q over KT delta potential. So it's the same. The terminology in chemistry is it's not exactly like in solid state physics, but it's the same behavior. The higher the potential the higher the deviation of the potential from equilibrium, the larger the concentration of the species where the reaction is going to. The electrochemical sign convention, the lower the electrode potential, the more readily it will donate electrons, which means negative electrode give electrons. Positive electrodes takes electron. So how do we measure potential? The way we measure potential in electrochemical sensors is by using a reference electrode. A reference electrode is what we call a true reference electrode, is ensure that any perturbation or measurement of the potential of the working electrode is based on a stable and known potential of the reference electrode. So the trick here in electrochemical sensors is that can we find some materials that we know the potential, and we put them into the same solution, and we measure versus this electrode. And since I know the potential from the textbook or from some table, then I know the potential of the solution. So in electrochemical sensors, what we do, since it's impossible to measure the potential of the system in equilibrium, what we do, we add another electrode. So usually we don't have two electrodes, we have three electrodes. we have electrode of materials. We call them reference electrodes. And the reference electrodes should be easy to use, and it should have a known and reproducible potential that somebody else calibrated for me, either Kelvin probe or other method. Once I have this electrode, if I want to do electrochemical biosensor or electrochemical sensor, I need to put in the solution 3 electrodes. One to measure the current or voltage or capacitance between them, and one to measure the potential. And I know this potential because somebody else calibrated it for me. And it should be stable, should be no chemical interference, and it has to be, the impedance can be very high if you want to chemically isolate it, or very low. Depends. Sometimes we take reference electrodes which are very high impedance, sometimes we have very low impedance. And we have if you ever do electrochemical sensors, which are very common today in many applications, you need to choose the reference electrode. And you have a selection. The supplier will give you silver chloride, platinum, and it will give you what is the known potential. So if you have the reference electrode, and 2 more minutes in your time, you know, if you have a 2-electrode system, we call one working electrode. You want to measure the potential because the potential of the electrode is proportional to what I measure. But as I told you before, I cannot put a potential, if I have 2 electrodes, I cannot, if I put here a voltmeter and measure the current, I cannot, nothing will come out because I will get 0. So what I usually do, I put 3 electrodes. My working and auxiliary electrode, which is like the positive and negative. And I also put another electrode I call the reference. Now, the good news about this reference, I know the potential of this electrode to here. Why? Because somebody sold it to me and somebody calibrated it for me. And I know the potential of this electrode to here. So if I measure it, I can know the potential between here and here. But I need to put a special apparatus. This is like a do-it-yourself potentiostat. I want to measure the voltage between here and here and the current between here and here, and to know the potential between here and here. If I know all of this, I know the potential between here and here and the current between here and here, and this is what I need. This is electrochemical cell. It's typical cell design, 2 electrodes. You don't see it much. 3 electrodes. Usually we have 2 electrodes and a reference electrode. There are electrical engineer in the house. So you do know what's a virtual ground? You know. How do you build an by the way, this electronics is called a potentiostat. Remember, the color, the silver one is the W, A is the negative, the other electrode, because if you want to measure current, you need 2 electrodes. You need to close the loop. And the purple is the reference. So what you do, you are applying, this is the reference, you connect it to an amplifier, so the voltage here equal to the voltage here. And what happens, you apply the voltage here, and there is a current, okay. And what happens when, and if you're closing the loop here, there's a current flowing from here to here. Oops. This is electrolyte here. The current is flowing from here to here. And this current is proportional to this voltage. So this potential you know the potential between here and here. So you can calculate the potential here. The current is flowing between here and here. And you know the current is flowing, so you can know the measurement. You can even do a better trick. You can connect your reference to this amplifier and connect, the current is flowing like this, and you know the potential here, you know the current through this. I need to know the current flowing between here and here. Because if I want to do electrochemical measurements, I want to measure the concentration or the chemical reaction, electrochemical reaction. So I need to apply voltage on the cell and measure the current. So I need to measure a current and the potential, but I cannot do potential direct. I cannot measure the potential between here and here directly. So I have to use this electronics to do it. And the reference can be small with high impedance. Could be effectively isolated. The reference couple do not have to be reversible. So this is practical how to make electrochemical. What I gave you until now is a kind of introduction to what is called electrochemical cell. I showed you what is the potential. I showed you how to measure the potential. I showed you how to measure the current. In the next lecture, I'm going to show you how to make a sensor out of it. So it's now 4:10, or 5:10, sorry. Let's get together in 10 minutes. Let's continue with sensors. The interesting part in the electrochemical sensors, that as you can see, the progress in electrochemical sensor was actually accompanied with the progress of electronics. Because if you want to do electrochemical measurements, if you want to measure the potential of something versus something in a liquid, which is very common in healthcare, in medicine, in agriculture, in environment, because in all these sensors, there's always some fluid, some liquid, even in air, there's always humidity in the air. So if you want to do potential measurements or current measurements, you need to measure the voltage versus something. And as I showed you before, you cannot do it with 2 electrodes, you need 3. So you need to have these differential amplifiers. So you need differential amplifiers. So 50 years ago, people used vacuum tubes, or 60 years ago, then people used semiconductors. But today also, the advances in computing, so people can do in real time the analysis, and also, for example, you can do the measurement of the potential in real time, and you can change the potential periodically, and then you can take the Fourier transform of the current versus time. So today, a lot of the signal processing has been transferred from the sensor to the computer. So using reference electrode became one of the key inventions that allow people to do this sensing. So what can you measure? You can measure electrode potential. You can measure transport. For example, you can measure transport of ions from point A to point B. By the way, one of the most common electrochemical sensors today is for diabetes, to measure glucose in the blood. And this is a few billion-dollar business. It did not exist 20 years ago. So, and also there are other electrochemical sensors for drugs, for proteins, for DNA. So it's become very popular. It's a function of many parameters of what you measure. Like I will not go through organization energy, but depends on the temperature, depends on the electrode material, depends on the distance between electrode and the moiety and the solvent. Potentiostatic measurement, as I showed you before, a true potentiostatic measurement is an equilibrium measurement. The classic example is the glass pH. You all remember what is a pH. pH is related directly to the concentration of protons in the solution. In neutral water, the concentration is 10 to the minus 7, so the pH is 7. So you take the electrode, you deposit the electrode. You can deposit them by sputtering, you can deposit them by plating, you can use the tools that I told you before. But you wrap it with a glass membrane. And one of the key factors in sensors is what we call selectivity. Because as I told you before, the electrodes depends on the potential of the solution. So if there is sodium, there is chlorine, there is potassium, there are many possible ions. Let's say I want to measure only protons. So what we usually do, we put ion selective membranes. I have to put a material that only protons will go through it. or only sodium will go through it, or only potassium. So to allow selectivity in electrochemical sensors, many times we coat them, or we put between the electrode and the solution an ion selective membrane. The reference electrode, typically made of silver chloride, this is one of the most common materials, because apparently silver chloride, which is silver coated with silver chloride, when you dip it in most solution, the potential is fixed. Depends only on the concentration of the solution. So if you calibrate it before, we know the potential of silver chloride for most solutions. So how to measure the potential of the solution? I put in a reference electrode, measure the potential versus it, and current is flowing between the two other electrodes. Okay, let's look again at this double layer thing. Assume an inert metal is immersed in the solution containing ions without any redox species. I don't have any redox species. So I don't transfer electrons. Just take a normal water, then you have protons and OH minus. I don't transfer electrons, just charge. So if I put a voltage here, negative, this charge negative, and the hydroxyl ions come close to the surface. And if I put positive charge, then the protons, then this will be positive, and so in this case, the hydroxyl ions will come close to the surface. Here, the protons will come close to the surface. What happens when a noble metal, I've seen this, I've shown you this before. So this is, okay. We are basically generating an interfacial charge. So in equilibrium potential, the potential of the working electrode versus the reference electrode will be defined by the Nernst equation, because I know the potential between here and the solution. And if I measure the potential of this electrode versus this solution, I can know the potential of this electrode versus the solution. Because this reference electrode is a special electrode, which somebody calibrated it for me. So I know the potential versus the electrode. And I know from the previous Nernst equation that the potential versus some reference potential depends on Kt over Q or RT over NF, ln the ratio of the concentration of the redox of the oxidation species versus the reduction species. What would be different about the system if the metal were different? What happens, the electrode potential can be set by adjusting the redox concentration or by adjusting the electrode. I can change this potential. By changing this potential, I change the concentration next to the electrode, and vice versa. Applying a potential will instantaneously change the redox concentration at the electrode. I mean, it's a very complicated way to say, if I put a positive charge, I attract the negative ions. If I put a negative charge, I attract the positive ions. This is a very much simpler way to say. Because remember, metal ions can be positive, and when I reduce them, I give them electrons, they become less positive. So the ions in the solution can be positively charged or negatively charged. So by concentration of these two ions, that depends on the potential difference between the electrode and the... So what happens is the following. Let's say the electrode is positively charged. When the electrode is positively charged, in the solution, we have ions. We can have, for example, minus can be hydroxyl ions, OH minus, can be chlorine minus, can be oxygen minus, can be bromine, iodine, many possibilities. But as I told you before, the solution wants to be neutral. We call this quasi-neutrality. So what happens, the negative ion will be surrounded by a positive charge, the average charge will be 0. And the positive charge will be will be surrounded by a negative charge. This is called solvation, which means this is an anion, negatively charged, and it's surrounded by average of positive charge. So the total charge will be approximately 0. And this is called solvation, which means when the ion is traveling in the solution, it's not just traveling by itself. Around the ions, there's always some charge from the solution, so the total charge will be 0. So the ion is not moving as a single ion, but as a solvated ion, which means when the ion is moved, the charge around it moves also. So what happens when it reaches the surface? The negative charge will be attracted to the surface, but next to the surface, there's not enough room. So it's very possible, so what happens here, this specifically adsorbed anion means this anion goes, and being adsorbed to the surface. It loses a lot of the solvated ions because they are plus, this is minus, electrode is plus, so the plus attracts the negative and repels the positive. So next to the surface, the ions will lose some of the solvated anions, some of this solvation. Now, other thing happens. What is water? Water is H2O. And H2O is a polar molecule. It has a side which is positive and a side which is more negative. So by symbolically, the negative charge will be closer to the electron and the positive charge will be outside. So next to the surface, we have an interesting phenomena. All the molecules of water next to the electrode are actually organized. They're not moving like a normal molecule in water is moving like in a Brownian motion. Next to the surface, it tends to have like an assembly of molecules. So what happens, this phenomena was described by Helmholtz, the famous Helmholtz from all the theory of fields, and he defined it as the inner Helmholtz plane. He said, let's define a plane that between this plane and the surface, all the molecules are organized and actually generating some kind of a dipole. And this charge is positive, negative is connected here, positive here, so all the dipoles is going, the dipole arrows is to this direction. So this layer actually behaves like an insulator. It's a monolayer or very close to a monolayer. It's actually, like a two-plate capacitor. One side is positive, one side is negative, so it's practically like an insulator, but it's a monolayer thick. Now, if you look at the solvated atoms, you find out that actually there is some charge around here. And he defines the outer Helmholtz plane. It's the plane where we have here a surface charge, because if this is a plus, this area on average is negative, because this positive, this is like a plate, a capacitor. One side is positive, one side is negative. So if the total charge here is positive, the total charge in this area will be negative to balance this charge. Outside of this plane, it's neutral. Now, this is a very symbolic notation. Of course, there's no, in real life, there's no sharp area between the charge and the neutral area. It's actually, the transition is smooth. And the width of this layer is the Debye length in this material. If you remember this from Introduction to Semiconductor Theory, it's the same phenomena. This is the edge. You have a space charge here, and this is called double layer. It's equivalent to, in semiconductor physics, to accumulation layer or inversion layer. But in semiconductor physics, it's electrons and holes, while in electrolyte, it's positive and negative ions. Anions and cations, but it's the same effect because it's the same Poisson equation, it's the same Boltzmann statistics. It's just instead of electron and holes, you have here anions and cations. And this area is called the double layer, and it has a capacitance because the charge of this plate depends on the potential. So what is the double layer? What happens? Let's plot, this is the metal, and let's plot the concentration of the anions and the cations in the solution. Now, in equilibrium, the number of positive ions is equal to the number of negative ions. So the number of cations is equal to the number of anions. It's like an intrinsic semiconductor when holes equals to electrons. So normally, C of one species is C minus is equal to C plus. When I put a zero potential, this is what happens. Now let's see what happens when I put a positive charge. When I put a positive charge, the concentration of the negative charge will go up. The concentration of the positive charge will go down. So net, I will get a net negative charge. It's exactly like an accumulation layer in a semiconductor or an inversion layer. It's actually basically the same equation, same modeling. I will not go through the modeling. It's very complicated, but it's the same modeling. What happens if I put more? Then I will have more. But the number of the positively charged cannot be less than 0. So it will be almost 0 next to the surface, but I cannot go more than 0. So what happens, the number of, if I want to have the total charge to be equal here, this area will be like, behave like a metal-like. It's not metal, but the concentration can be very high. But don't forget that the concentration here can have a certain maximum because molecular weight of water is 18 grams per mole. So in 1 liter, you have 18 moles. So if every molecule of every molecule of water is replaced by ion, I cannot have more than 55 moles per liter, or approximately. So the concentration on the surface also is bound, because I attract so many ions to the surface, so each ion is replacing water. There's no water at the surface, only ions. But I cannot have more ions than a certain volume. So this is the effect. And if you look at the potential, you find out that between, this is the inner Helmholtz plane, and the metal, we have a layer which is typically about half a nanometer or 0.7 of a nanometer, up to 1 nanometer, which is the dipole. And over there, there's no charge, there's just dipole. And outside this, we have the double layer. And the potential here, because it's a dipole, the potential drop on this layer, I want to remind you, what is this layer? This layer is a dipole layer. Because here and here, we have only dipole, because all the water molecules are organized next to the electrode. So in this dipole, there is no charge inside, so the potential drop is linear. So, and the electric field is fixed. It's a dipole layer. It's not a single dipole, it's a dipole layer. It's a layer of dipoles. However, outside, between the edge here to the electrolyte, the potential drops, and it drops exponentially. And the distance here is approximately the Debye length. So if you look at the model of an electrode touching an electrolyte, you have 2 capacitors. The capacitor of the double layer of the inner Helmholtz plane, we call it, I put here Ci, and which is Ci is from electrostatic theory is the charge divided, the potential Phi times the capacitance Ci is the number of charges. This is a simple definition. So in order to calculate Ci, I need to know this potential difference and sigma. And this double layer capacitance depends on the potential. So the total capacitance here is this capacitance in series to this capacitance. But you can calculate from basic principles, you should solve the Poisson equation, and here's an expression calculating the double layer capacitance versus the potential, but this is not the main importance of this class. So C total is typically in the range. Now in flat capacitor, the capacitance is 5 to 20 microfarad per centimeter square. This double layer capacitance is typically 5 to 20 microfarad per centimeter square. Now, if you take a parallel plate capacitor, like MOS device gate or a gate in a circuit, typically the capacitance will be 10 to the minus 8, 10 to the minus 7 farad per centimeter square. Here, it's 10 to the minus 5. This is why electrolytic capacitance is so high. And if you have a high surface area, if you roughen the surface, if you take nanoparticle surface, then it can be more than 100 microfarad per centimeter square, which is huge. In MOS capacitance, like a gate oxide of 6 nanometer hafnium oxide with a permittivity of about 24, C oxide is 0.3 microfarad per centimeter square. So it's a huge capacitance. So what are the effects of the double layer? What I'm going to do now, this is the introduction. There's a large set of slides which are discussing the basic electrochemistry and the typical electrochemical reactions, Faraday law, feasibility, electron transfer. This is a background, so if you want to read it, if you don't want, you can skip it. This is introduction. I put it so if you really want to know basic electrochemical methods, you should read this. I'm not going to do it today. I could hide the slides, but I'm not going to do it. So I want to go to the practically. I promised you we talk about sensors. So this is the introduction to electrochemistry. The last slide, which I apologize, I did not put it on the. I forgot to upload it, and I will do it tonight. Is the nanoparticles and sensors. It's a short presentation because I gave you introduction to electrochemistry for about 40 minutes. Now, how do we use it for sensor? And how do we use microparticle and nanoparticles? And this is like nanoparticles and sensors. And it's related to electrochemistry because I'm not going to talk too many sensors, but I'm going to focus on nanoparticles. As a sensor, as I told you before, sensor that we sense a phenomena. An electrochemical sensor, this is a sensor that is using electrochemistry for sensors. And biosensors is when we want to detect biological phenomena. This is a huge class of sensors, and actually one of the biggest classes of sensors because it's used from enormous amount of materials. So I decided to choose this one because it's very widely used. So a biosensor is a detector based on selective molecular components of plants and animals. And practically, you can take two different disciplines which impact biosensors. First is molecular biology, the biggest recent advances in molecular biology. And the second one is information technology. Most of new biosensors use microfabrication and nanofabrication methods in addition to molecular biology. So one of the things that happened in the last 20 years when I was working on, we worked on nanotechnology, we just didn't call it nanotechnology, we call it deep submicron technology, and then we found out that people with biology are actually using the same techniques. So it's a lot of activity in this field. People use it for healthcare, environment, agriculture, and security. What you can detect in biosensors. And by the way, people use it in pharma, food industry, homeland security, agriculture, environment. Practically, biological recognition elements. As I told you before, a sensor, the key component of a sensor is the transducer. So what you can detect? You can detect enzymes, antibody, macrophage, and cells. These are typical molecule biologies that are being detected. And you can, it's a little bit small, but you can change you can look at the electrodes, semiconductor electrodes. You have the signal transducers. You can, for example, you can make these biological reactions emit light, and you can use photodetector to detect light. You can, one very interesting device is that you measure the mass of you make a micro machining a very silicon beam, and when the molecules are attached to the beam, you change the mass. Now you know how to detect mass because you measure the vibration frequency of if it's a pendulum, and you know that the vibration frequency of a pendulum depends on the mass, on the mass of the pendulum.
and you can measure frequency with great accuracy. So you can measure mass. This is called like a microbalance. So there's a lot of effects to do what we call biological recognition elements. We can detect enzymes, antibodies, which are very common for antibody-antigen reactions. You can detect nucleic acid or a whole cell. And the principle of biosensors are the following. You take, let's say you have a biocomponent. You want to detect glucose. How do you detect glucose? You put a molecule which reacts with the glucose. So you have the substrate, and the glucose, we call it substrate. And this is the definition of chemist. Don't blame me, because for me, a substrate is something that I put a wafer on top of it. For chemists, a substrate, this is the chemical for reaction. And by the way, when I started to work with biologists many years ago, I found out that they speak completely different language. I really need to translation. So in this case, the substrate is the chemical to detect, in this case. And in this case, it's glucose. So I put here a biocomponent which identifies glucose. And this is an enzyme called glucose oxidase that we all have in our body, because the glucose oxidase in our body interact with the glucose and break the glucose and use it to generate energy. This is how we live. Sugar is part of the components that our body digests and convert to energy. So I put here a biocomponent which specifically reacts with glucose. And it generates a product. Now, there are a few possibilities. One product is hydrogen peroxide, H2O2. And I make a detector of the product. So I make a detector to detect H2O2. By the way, one way to detect it is to change color. There are some components that H2O2 it's a very oxidizing component, so I can do a change of color. Or I can reduce it. I can actually put an electrode, and H2O2 really wants to be converted to H2O and oxygen. So I can apply potential to encourage it to encourage the oxidation reaction. And then I take the current flowing and amplify, do data processing and storage. The second option is I take a biomolecule, like antibody. An antibody typically is made of like structure with like two horns. So when it catches the antibody, I have a detection. This is for example, how our body identifies components. It's called the antibody-antigen reaction. So I put the antibody or the antigen directly on my electrode, and if there is a hybridization reaction, I can also use it to detect DNA, because DNA, you know, the DNA always has for every short chain of DNA, it will bind completely to another chain which is the opposite. So I can use this biomolecule. I use a hybridization charge, and I put it on an electrode. So when one molecule is adsorbed to the surface, I change the capacitance. I can measure capacitance. I can measure the electron conduction. I can measure the resistivity of the structure. I can use physical phenomena to detect it. And I can use electrochemical reaction. So a typical biosensor, and I took it from this paper, you can have, there are bioreceptors. Cells, basically cells are receptors. Our cells are detecting materials, or DNA. And this is the antibody-antigen reaction. The antibody in our body, which is part of the immunization system. And what they do when we are attacked by a disease, the antibody identify the disease. But I can make antibodies for many components. So I can use this antibody as a sensing component. And enzymes are very popular biosensors because enzymes are very specific. Then you have electrical interfaces. You have electrodes, which you use on a nanochip. And then you have nanoparticles, nanotubes, and the electrodes. And then you have the transducers,
which are converting the signal to a light, to a magnetic field, optical field. You can think about transducing this effect into this effect, and then you take the information, do signal processing and display. And the big revolution in the last 20 years is that we can do everything on a chip using the same technology that I told you in the first 6 or 7 lectures. Now, specifically, I want to dedicate the next few minutes in using of nanomaterials. Why using nanomaterials as nanosensors, as biosensors? First, they have very high surface to volume ratio. They have high surface area. And also they have very specific electro-optical properties, and they have increased catalytic activity. Let me 1 minute about this catalytic. When you want a chemical A to react with a chemical B, we have some reaction rate, which means the reaction occurs at a certain numbers per second. And I can increase the reaction rate by using an effect which is called catalysis, which is making the reaction more favorable by reducing the activation energy of the process. And so it happens that nanoparticles, by nature, most of them have higher catalytic activity. If you are using palladium, for example, and you use in your cars palladium to break the gases in the exhaust system, so it will be less toxic. This is called the catalytic converter that we all have in our cars. If we use nanoparticles of palladium instead of regular palladium, the catalytic effect will be much higher, and I can use much less palladium. So people switch for a long time. Instead of putting a big piece of platinum or palladium in your car, which makes your car too expensive, they use nanoparticles or some mesh to increase the surface area. And because of the larger catalytic properties, they have enhanced energy electron transfer. Now, there are many nanomaterials for biosensors. There are fullerenes, carbon nanotubes, dendrimers, liposomes, quantum dots, and metal nanorods. And this is a dendrimer, this kind of structure. You can take, for example, this is a gold nanoparticle that you link to it an antibody. So this gold nanoparticle, which is a metal, now it has activity like an antibody. So if there is the antigen next to it, it will bind and you can detect the antigen. So you can use it, for example, to detect diseases. If you want to detect a certain microbe or a certain virus, you can use the antibody to detect it, and then you have to detect the gold. This is called labeling. This is called sensors which are labeled. I don't detect the microbe, but I connect the antibody which detects the microbe, and this antibody is connected to the gold nanoparticle. So once the gold nanoparticle is attached to the microbe, now I can detect the gold. How do you detect gold? You use, for example, the effect that gold has a very high atomic mass, so it's easy to see it in X-ray, and gold is also easy to see in other techniques. So you detect your biological target by attaching it to a gold nanoparticle or other nanoparticle, and this is called labeling. So this is a very common technique for sensors. So the key parameters are sensitivity, minimum detectable signal, stability, reproducibility, accuracy, and precision, as we talked about it before, selectivity and cost. It's the same. For every sensor I'm going to teach you, it's going to be the same list, almost. Yes? You can ask in Hebrew. Okay, let's say I want to detect if I have influenza. So I take a sample of my blood, and what do you want to do? To detect viruses of influenza. So I go and I ask my friend, can you give me some antibody of influenza? And he said, no problem, I have antibody of influenza exactly from the right type that I need to detect. So I mixed my blood with nanoparticles, but to the nanoparticles of the gold, I bind the antibody for the influenza. Then after a certain time, it can take a few minutes or a few hours,
the viruses will attach to the gold. Now, what I'm doing the following. I can now I want to detect the gold, which is now the gold is attached to the virus. So what I can do now, I can separate the gold nanoparticles which are not attached to the gold particles which are attached. They have a little different weight. I can do it by centrifugation, for example, or by filtering. And then I need to detect the gold. Now, it's much easier to detect gold than to detect viruses. Why? Because gold is a very high atomic weight. I can use it for in X-ray to have a beautiful signature. I can use other methods to detect gold. Instead of gold, by the way, I can use iron. People use today a lot, instead of gold, using iron oxide. Now, iron oxide is a wonderful property, it's magnetic. So what they do, they mix the blood with the gold nanoparticles, and they take iron nanoparticles, not gold, mix it with the antibody, mix it with the microbes, and then wait, and then use magnetic field, and all the gold is attracted. Now, I can see gold with antibody and microbe, and gold with without will have a different color. This is a phenomena called plasmon resonance. The color, the reflection of nanoparticles depends on what's attached to the surface. So I know if this yellow is this yellow, you're healthy, it's a different color. So the trick is you label your nanoparticle with what you want to detect, then you detect, and then you don't detect what you want to detect, but detect the nanoparticle. And use physical method to detect gold, because easy to detect gold, easy to detect iron. But you don't care about iron or gold, because you care the iron is bonded now to the virus, or not, and you can see a difference. This is called labeling. It's one of the most common way for sensors. And I wanted to tell you more about nanoparticles for biosensing. So we'll take 2 minutes of your time. And this is the idea. You take the nanoparticle, you connect to a DNA, protein, and cells. And you can either use optical detection, because nanoparticles have very specific optical properties, which depends on the size. Because when the nanoparticles is very, very small, it can behave like a quantum well or has a plasmon resonance. They have different color, different shape, different optical properties. And when they bind to biological species, they change their color, transparency, luminescence, etc. Or you can measure their electrical properties. You can measure electromechanical conductivity. Their potential is changed because previously it was only gold. Now it's gold plus virus, gold plus protein. So the potential of the nanoparticle change versus the solutions, and you can measure it. We are running out of time, so I'm going to two more. I think I'll just show this slide, and then the idea is the following. Let's say you have your bioreceptor, and you can look at the catalytic properties or affinity. Affinity is the attachment, how strong your target likes your label, likes your antibody-antigen reactions, the reaction is very strong. But some surfaces, for example, if you put, some reactions are very, very weak. So you have the interaction between antibody and DNA, or enzyme, or the cells. And then you have, practically, you can deposit them on electrodes using covalent bonding, cross-linking, adsorption. And I think this part is what we are looking for. But the idea is the following. We have the electrode as I showed you before. And the electrodes, I can bind to them the molecules. So I can do electrical detection. But I can also look at optical properties, because the nanoparticles, their optical properties depends on the detection. Also physical, like piezoelectric and temperature. So I think we'll stop here. And the rest will be free reading. It's a lot of slides.
if you want to read them all, we actually covered only 16 slides, and I put like 161, so we still have 100. So we're not going to cover it by this lecture. I'm going to put this on the website as a reference. If we want to know more about nanoparticles and biosensing, you're invited. This is just an introduction lecture, so I give you just a taste of what are sensors and how complicated are these topics. Maybe next year I will give a whole semester lectures on sensors, so this will be part of it. And next week we are going to have an invited lecture. Professor Danilo De Marchi from Torino, and he is a world expert on a very special sensor which is called nanogaps. Today I gave you a little bit a glimpse on nanoparticles, and he's going to talk about nanogaps, which are actually becoming more and more popular as leading technologies. So we decided to teach. It's going to be a very useful device. It's still under research, but it's one of the most promising devices that exist today. And then we continue with the rest of the class with me and Yaakov until the end. And I owe you a few lectures. We are going to give pay attention. We are going to give more tutors, more tirgulim, more exercises. We owe you 3 exercises, and Lee will coordinate it with you. So this is it for today.